In this example, we're going to be calculating the moment of inertia about the x-axis of an object that's composed of two different flanges. You see there's a flange up top that's 6 inches by 2 inches. We have another flange at the bottom, which is 12 inches by 2, and then we have this centerpiece here, which is, let's see, this piece is 6 inches tall by 2. Okay, so that's the web, and then we have the two flanges. Okay, now the approach that we're going to be using is what we learned in the PowerPoint, and that's the parallel axis theorem, which states that the moment of inertia about an entire body is equal to the sum of the moment of inertias of the individual pieces, in this case about the x-axis at the centroid, plus the sum of the area of each individual piece times the distance squared. And the distance that we're looking at, this dy term, is the distance between the actual centroid of the component and the centroid of the overall object. Okay. Now what I've done is I've done kind of a simplified drawing over here. And the x in this drawing represents the centroid of each individual component. Okay. The c right here with the dot represents the centroid of the overall object. Now that was given to me as having a coordinate of 6 in the x direction and 4 in the y. So what I did is I drew this dimension 4 inches right here, which is again the y distance from the bottom flange to the centroid. And what we're looking for, before we go ahead and do the table, we're going to go ahead and figure out what these dy distances are for each piece so that we can fill out the table. Now, let's look at this bottom flange right here. Okay, this flange is 2 inches tall. So the distance to the centroid of that is 1. Okay, so the distance basically from here to the x, right, to the centroid is 1. So if this entire distance is 4 and we subtract out 1, that tells me that this dy right here is 3 inches. Okay, now let's look at the top flange. The overall object has a height of 2 plus 6 plus 2, which is 10. So this whole height is 10. If we go down 1 inch, that would take us to the centroid of this particular flange right here where we have the x. So that tells us that this total distance from the bottom of the object to the centroid of that top flange is 9. So if this distance is 9 and this distance here is 4, that tells us that the dy, the distance from the centroid of this top flange to the centroid of the object, would be the difference between the two, and that's 5 inches. Okay. The last piece we need to look at this little web. Okay. This web is 6 inches tall by 2 inches wide. Okay. Now, to find out the height from the bottom to where the x is, the height to the centroid of that web, we have to add the 2 inches here. And then if this whole height is 6, half of that would be 3. So we would have 2 plus 3, or total distance of 5 inches from the bottom here to where the x is for that center web, for the center of that web. Okay. If this distance is 5 and this piece right here is 4, that tells us that this distance here is the 1 inch. Okay. So now that we have these distances figured out, the dy terms, let's go ahead and work on the table. When I set the table, the first thing I'm going to do, of course, is have the 3 components. So I've got this top flange here, which is 6 inches by 2 inches. I've got the middle web. Okay, this is 6 inches tall by 2 inches wide. And then I've got the bottom flange, not really drawn to scale, but as long as I have dimensions in there, I think we can work with it, which is 12 inches wide by 2 inches tall. Okay, so the first thing we're going to calculate is the moment of inertia about the x-axis at the centroid. Now, for a rectangle, the general formula for this is 1/12 times the base times height cubed. Okay, so for example, for this first rectangle, it would be 1/12. The base is 6. The height is 2, so that's 2 cubed. Right? So 6 over 12 is basically a half, times 2 cubed is 8, so that comes out to be 4. Okay? Let's do the same thing for this rectangle. So we have the 1/12, the width, the base is 2, the height is 6. Okay? So if we have 2 over 12, that's 1 over 6, and then we have 6 cubed, so that comes out to be 36. Okay. And then on this one here, we're going to have the 1/12 times 12 times 2 cubed, which will come out to be 8. Okay. So again, for each of these individual components, we've calculated the moment of inertia about the x-axis at the centroid. Now, for the area term, this is pretty straightforward. We have an area of 2 by 6, which is 12. We have another area of 6 by 2, which is 12. And then we have an area of 2 by 24, which is 24. Okay. And then the dy terms we just calculated earlier. So for this top piece, the dy is 5 inches. For the middle web, it was 1. And then for the bottom flange, it was 3. So now all we have is some math. We're going to take the area this area term times dy squared to get for this last column. So I've got 12 times 5 squared comes out to be 300. I've got 12 times 1 squared, which is 12. And then I've got 24 times 3 squared, which is 9. That comes out to be, let's see, 216. Okay. Now, according to the formula, I need to sum up these terms, right? I'm going to have to sum up the moment of inertia term, right, here for each individual component. So I have 4 plus 36 is 40 plus 8 is 48. Okay. Here, I'm going to have 300 plus 12 is 312 plus 516 is going to be 528. Okay, so I've summed up those terms. And so right now, we're going to finalize the calculation, okay, by summing the sum of the individual moment of inertia terms, which is 48, plus the sum of all the area times the distance squared terms, 528. Okay. And this will give us 576. And the units on that would be inches to the 4th. Squeaky marker. Okay. And that concludes this example.